Good evening and welcome to the Italian Cultural Institute. Buonasera e benvenuti all'Istituto Italiano di Cultura. This evening's event is part of the Giornate della Scienza, Science Days, that the Ministry of Foreign Affairs decided to formalize, if you want. They decided this year to have a formal moment to acknowledge the importance of scientific cooperation between different countries and the importance of the international exchanges between Italian scientists and scientists from other countries, exchanges that in many instances turn out then to make many scientists decide to continue their work abroad, as it happened with the previous event that we hosted last week. We hosted another event for the Giornate della Scienza to medical doctors talking to pediatric oncologists talking about their research on cancer, brain cancer. A few remarks about why in this date, why now the Giornate della Scienza. The ministry picked the birth date of Leonardo da Vinci. We have to go back several centuries in time. Picked the birth date of Leonardo da Vinci as the focus of the Giornate della Scienza, the annual, this annual appointment, which we celebrate now for the first time, which is the first edition. Leonardo da Vinci was born on the 15th of April, 1452. And I also, since we're talking about anniversaries, I also want to mention that this year is the anniversary of the Constitution, the coming into effect of the Constitution, and I want to point out, since we talked about that, that the Articolo 9, the 9th article of the Constitution, promotes scientific research. Says that the Italian Republic promotes scientific and technical research. So it's really something that's, that was acknowledged at the core of the principles on which the new Italian state, the Italian Republic, was established. So before leaving the floor to our very welcome guest, just a few remarks on his exceptional career. Dr. Giuseppe Cataldo, who kindly accepted our invitation to come here from Washington for the first edition of the Giornate della Scienza, which we organized, by the way, with ISNAF, the Italian Scholars and Scientists in North America Foundation, and I want to thank the representative of ISNAF for contributing to these events. Dr. Cataldo earned his bachelor's degree in Milan at the Polytechnic in 2007, and then he earned his MA in the same field, aerospace and aeronautical engineering, from the Milan and Turin Polytechnics, jointly with a prestigious French institution, Super Euro, in Toulouse. And then he came to the States to earn his PhD at MIT in Boston. In the meantime, while still a student in the MA program, he started working with NASA. So, and then he joined NASA in 2009 as one of the 2 Europeans selected by the European Space Agency. Since then, Dr. Giuseppe Cataldo has contributed to a variety of NASA missions and projects and has received several awards, including NASA's 2017 Early Career Public Achievement Medal. He is currently a space system engineer for the James Webb Space Telescope, working on projects that, besides aiming at the spatial and temporal limits of the universe, I was glad to come to know that they also generate technological advances relevant within our more pedestrian, earthly horizon. For the majority of us who stand in awe of the dark, silent worlds that some of us, fortunately, dare to explore. So please join me in welcoming Dr. Cataldo.
Good evening, everyone. It is really my pleasure and honor to be here tonight. So thank you very much to the Institute for inviting me here tonight and for making me a part of this first edition of Science Day that we are celebrating all over the world. So tonight I would like to really take you on a journey that goes from, well, Leonardo da Vinci's birth all the way to James Webb, the telescope and the person. So you will hear more about it later in my presentation. And then, yeah, so it's just like a story, and I'll tell you more about what we have been doing to build such a jewel of engineering that we are going to launch in 2 years, so really, really soon. The journey starts with Leonardo, 1452, and I think, as Donatella mentioned before, the ministry couldn't have chosen a better figure of Italian genius to really celebrate all these accomplishments. He was a painter, a sculptor, an architect, an engineer. He was curious just about anything, and all he could observe, he would just, delve into it and try to understand what was behind it. So he really tried to apply his creativity, his genius to everything that would have a graphical representation. So he liked really, to wonder about our universe. What is it all about? And so, that's why he ended up doing anything, pretty much, from painting, anatomical studies, drawings, mechanics, cosmology, even tried to build, flying machines like those that you see here in an attempt to, try to understand, am I right? Do I understand this phenomenon the right way? Can I make it happen? Is that how nature really works? And I mean, it was really, I think, a really big push to, science. And I mean, close to him, we have Nicolaus Copernicus. A few years later, well, we went from wondering about our universe to trying to understand our universe. I think probably you all know about the Copernican revolution. It was a revolution at the time because everybody thought that all that we see in the sky rotates about our planet. So the sun, the stars, everything rotates around us. Well, Copernicus said, well, I don't think that's the case. And he said actually that what happens is that the sun is at the center of the system, and then we have all the planets orbiting around our star. So really, it became, he understood how planets move, and that was a revolution because that meant that in order for the planets to orbit around the sun, there had to be a force that the sun would exert on all these bodies to be able to keep them in motion around it. So the first concept of gravity, the force of gravity that keeps us here, grounded on planet Earth. So astronomy, physics, but also philosophy. Man was no longer at the center of the universe. We are no longer the center of everything. There is something more out there that we are only now, back in those days, trying to understand. And then a few years later, Galileo Galilei. So from wondering to understand to observe our universe. Galileo was the one that pointed for the first time his telescopes up to the sky, and he saw a lot of things, from the moon to Jupiter, and the 4 moons that he discovered, we still call the Galilean moons. But not only that, he went on and saw the Venus, Saturn, and Neptune. Those are Saturn and Neptune are like some of the furthest planets in our solar system. So a lot of discoveries, a lot of questions already, over 500 years ago. Why do we look up at the sky and we see all these things? Well, now we are going to fast forward a few years. We arrive at 1929 when Edwin Hubble actually argued that the universe is not static. The universe is expanding. The universe is growing, getting bigger and bigger, larger and larger. And he was able to do so by looking at some very distant galaxies and realizing that these galaxies were actually getting farther and farther from us. So they were not just fixed in the sky like they made appear to us, but they were actually getting farther away. You probably know that we are going to celebrate in just 2 days the 28th anniversary of the Hubble telescope that was launched on April 25th, 1990, and that's the telescope right there. That was named after the scientist Edwin Hubble that made that discovery in 1929. All these discoveries were really disruptive. They were changing our understanding of the universe. And clearly, the early 1900s were years of intense study. A lot of discoveries were happening. Something like this that we were able to achieve only 40 years ago, actually 6 years ago, that's what Hubble gave us, one of the most, beautiful pictures of our universe. Those galaxies and points in the picture are some of the oldest and farthest objects in the universe. Now that's really how far Hubble was able to go. It's telling us, look, there's a lot of history out there. So when we look at the sky, we are looking at our history, at things that maybe by now do not exist anymore. Okay, but we still see them. The light's traveling to us, and it takes time to get here. And that's one of we call it the extreme deep field. Hubble looked very, very far away, and far away in space and far away in time. So, what is the best explanation of all this so far? We try to answer all those questions, and I think we are all familiar with the Big Bang Theory. The Big Bang Theory that actually was, created 2 years before Hubble made that big discovery of the expansion of the universe. It was a Belgian Catholic priest, Georges Lemaitre, that actually came up with the idea of the Big Bang. It was the one that derived Hubble's law, even before Hubble, like I said, 2 years before. And he published his paper right away. He didn't want Hubble to, to do it before him. And he was the one that was able to apply Albert Einstein's theory of relativity to, the expanding universe. And he said, well, if the universe is expanding, well, that means that if we go back in time, then everything will just, in just one tiny, tiny point of matter and energy, everything was in there. And then probably all of a sudden, everything exploded, the Big Bang, and started to, travel in space and getting farther and farther, like we have been saying so far. Well, I think so far, this theory still holds. We have built a lot of satellites and made a lot of measurements that prove many of the ideas behind the Big Bang theory. But yeah, as I said, still a lot of issues remain open. We are not done yet. Scientists still have a lot of work to do to answer many more questions that the Big Bang theory is not able to answer. And who knows, maybe there is something wrong in this theory that we still cannot understand right now, and that we will in some years from now. And some of the questions, what happened before the Big Bang, and like that, many other questions. All right, so in a nutshell, I'm gonna give you an idea of the history of our universe in just a minute. I will try to do that. So the universe is almost 14 billion years old. That's the age of our universe, 14 billion years. So we are right here. That's right now, 6 o'clock in New York City. Okay, and we go all the way back to the very origin of the universe, the Big Bang. That was 14 billion years ago. So let's start from here. Like I said, Big Bang, there was a big explosion, followed by what we call an inflation. Inflation means like a very rapid expansion of the universe. Like a fraction of a second, the universe is already trillions of miles across. After 3 minutes, we think that the first atoms of hydrogen form. After only 3 minutes. And the universe already, I think, something like 300 trillion miles across, huge. At that point, everything was still very complicated. It took the light about 400 million years before it could separate from the matter and travel into the universe. That's why here you see the Dark Ages. For 400 million years, the light was entangled with the matter. It was just, there was no light. The universe was really dark, literally. And after the point where the light was able to disentangle from the matter, in simple terms, at that point started to travel across the universe and to reach, us when we look at the sky at night. So that light comes from here, from this moment here. When the universe was 400 million years old, I was still a baby. Really a baby if you really think about it. So, and then from there, that's when we started to see the formation of the first stars, the first galaxies here that grew more and more across eons and many years. Galaxies, planets, solar systems like ours formed. And in the meantime, we noticed that the universe was expanding. It's not just a flat line here, it's actually growing, getting bigger and bigger. And it's doing so in an accelerated way. It's expanding and doing it faster and faster. So that's very important for all of you to understand, because James Webb Telescope is going to tackle all these questions about the origin of our universe. And so like I said, keep in mind, we are here, the first light was born here when the universe was 400 million years old, and before then, like I said, there was no light, so there is no way we can look at what happened before that moment with any telescope. But we need to use something else called gravitational waves. And so that's what we need to understand what happened in the first 400 million years. But tonight I'm not going to talk about gravitational waves. That's for some of my colleagues to talk about it. I'm going to focus on the first light. Right, so how does everything work? So when we have a star like this that emits light, the light travels, right? But then you might have, you know what happens when it rains. We are all familiar with the rainbow phenomenon in the sky. So it rains, and all these drops of water, maybe diffract the light into a rainbow, what we call a spectrum of light from red to blue, with all the colors in between. So imagine that, that's like our sun. Okay, what happens if between the sun and us there is a cloud of cold gas? Okay, which is the case up in space. It's all very cold out there. Well, we see something like this. We see some like dark lines in the rainbow in the sky, kind of, right? And that happens because some of the atoms in the, in this cloud of gas absorb the light at certain wavelengths. So they absorb the light. Sometimes they re-emit the light at the same frequency. And that's when they re-emit those lights. So here they disappear, they become black, which means that we don't see them. And here they reappear magically, okay? So these lines, they tell us what kind of chemical composition the star is made of, basically, okay? So we know, for example, this line can be, I don't know, hydrogen. That line can be carbon. That line can be oxygen. So we know each line very well, and we know all the chemical elements that each line is associated with at a certain wavelength. Now that's very important because what I said before, we are looking at things that are very far away from us and are very old. So if we have all these lines, and like I said, we know those lines very well, then what astronomers do is they try to look at the same thing, but like in the sky. So they look at a nearby star, and it's in the same lines, but you can see that those lines don't overlap anymore, right? They are shifted a little bit. And then if we look to a nearby galaxy that's even farther away, those lines are shifted a little bit more, and so on for a distant galaxy and for a very distant galaxy. So what do you notice in this pattern here? That all these lines are being shifted toward the red. And that's what we call the redshift, right? So all these lines are moving slowly toward longer wavelengths that are red. So that's what we call the infrared, right? So that's like what we can see with our eyes. And then here we get to a point where we can't see beyond this. And so that's what Hubble saw. Hubble saw that every time we look at a star, a galaxy, a distant galaxies, all those lines were shifting, and that told him that, hey, things are moving farther away from us. Actually, all of us experience the same phenomenon here on Earth when you hear with your ears, like an ambulance go by. So you hear, if something's not moving, you hear the sound the way it is. But if an ambulance passes by very quickly, you're going to hear a sound that changes, right, as the ambulance goes by. The ambulance is moving, and so the sound that you hear at the beginning is not the sound that you hear after the ambulance, has passed by. So that's the same idea behind this plot here. So the galaxies get farther and farther away, and therefore their wavelengths, the wavelength they are emitting, gets shifted toward the red. And that's very important because the very first galaxies they were trying to look at and to learn more about are exactly in this regime here. They're all redshifted by a lot, and that's one of the tasks of James Webb. So we understand also that most of the energy of the universe is exactly in the infrared. And that's why we really want to look at all these infrared emissions. Unfortunately, we cannot do it from the Earth because the Earth, our planet, the atmosphere of our planet, absorbs much of the infrared light. Okay, here, it's absorbed from our planet, so we can't really look at anything here. We need to go in space and put our telescope up in space to be able to look at this infrared light. But now, why do we care about the infrared? Or actually, why is the infrared so cool? No pun intended, because if we look at this nebula, that's how we would look at it with our own eyes. These are true colors. Okay, that's like visible light. You take a telescope, you look at it, that's what it would look like. But then if we look at the same thing in the infrared, look, it looks completely different. What is the main difference between this on your left and this on your right? Well, look how many stars are in this nebula, which we cannot see. So a nebula is making a cloud of dust. That's literally interstellar dust, clouds of gas and dust that we cannot just penetrate with our eyes. But the infrared can. The infrared wavelengths allow us to penetrate what's hidden behind these clouds. And look, a lot of stars that are forming. So, the infrared really provides us with a tool to probe such phenomena that happen in the very early universe. Okay, so that's the same picture that I showed before. What we want to do at this point is try to understand. So that's the Big Bang, the Dark Ages, the first light. We want to have a telescope that is capable of looking all the way back to the very first light, in the infrared. Because the infrared will allow the telescope to look that far, even farther than Hubble did, and therefore be able to look at these first objects in our universe and learn how stars and galaxies were formed, and eventually how we came to be, why we exist, how come that there's life here on Earth, how come that the Earth orbits around a star like the Sun. So all these questions about galaxies, about stars, planets, what are the building blocks of life? These are the questions that we are trying to answer, that we want to answer in the next few years. So here we are with the future of astrophysics called the James Webb Space Telescope. I don't know if some of you have seen this, but that's something that we have built. It's no longer just a picture. It's something that exists in reality, and we are in the process of assembling together and testing right now. As I mentioned, it will be an infrared telescope that will launch not earlier than 2020, so hopefully in 2 years from now. And it will be the successor to the Hubble telescope. Like I said before, Hubble is still going very strong, 28 years and going. Hopefully we'll have the two of them work together for some time. And I want to emphasize that this is an international collaboration between NASA, the European, and the Canadian Space Agency. So we have really thousands of people working on this project. And really, I always like to tell an anecdote. When I go home in Italy, where I grew up, I like to compare my science textbook with my brother and my sister science textbook. They are younger than me, and just a few years later, what they studied in school is so much different from what I studied when I was their age, thanks to Hubble, the discoveries that Hubble made in just 5-10 years. It's amazing. So I can't even imagine what we are going to be able to do with James Webb. So now I'm going to talk a little bit more in detail about James Webb, how it works, and what it will be able to do for us. So there are different parts. The yellow part up here is the main mirror. It's like our eye, the eye of the telescope. That's a big mirror here, and there are smaller mirrors up here and in the back. Then that's the mirror that will collect the light. Then the light will go all the way in the back here, this black box, in the back where we have the brain of the telescope. So all the instruments that will analyze the light and will tell us what the light means, where it comes from, and try to answer all those questions. So the mirror, the instruments, and then this big sun shield. In a shield that will protect the telescope from the radiation of the sun. And that's up down here. The spacecraft bus is what will allow us to communicate with the telescope. But before we dig into the details, who was James Webb? Like Hubble, he was a real person. And so we decided to name the telescope after him for the great contribution that James Webb did to the science program. James Webb was the second director of NASA, the second NASA administrator from 1961 to 1968. So those were the years of the Mercury program, the Gemini program, the Apollo program that eventually led the man to the moon in 1969. He was a great guy, and he really pushed the science program of NASA so much that thanks to him, I think there were about 75 space science missions that were launched that happened under his administration, imagine, back in the 60s. And he was not even a scientist or an engineer. He was a lawyer who worked for the State Department, the Bureau of the Budget back then. But he was really loved by President John Kennedy and President Lyndon Johnson, who gave him really a lot of power to really make of NASA, the great agency that it's now. NASA was born only 3 years before 1958, so we're really at the very beginning of NASA's history. So I think we really owe this to him. So like I said, the mirror is the eye of the telescope. So we have the light, the main light, that's collected by the main mirror here, gets reflected to the secondary mirror here, and then eventually back into the black box to go into the instrument. All right, well, you can see that this mirror has, it's made of smaller mirrors. It's not just one big piece like Hubble. It's made of 18 smaller mirrors. You can see them all here with the shape of a hexagon. And, well, anybody knows why we did that? We thought that, well, for many reasons. First of all, the size of the mirror is 6.5 meters. It's really, really big, almost 3 times bigger than Hubble's mirror. But on top of it, you may remember what happened to Hubble after we launched it. After we launched Hubble in 1990, all the images that we're getting back from Hubble were kind of blurred. They didn't really look nice, and we said, well, what did we do? What did we just launch up there? Like, really? And, well, back then with the space shuttle, we were able to launch a few astronauts. Went up there, grabbed Hubble, and they changed the mirror, the main mirror. They could do it because Hubble was still orbiting about like 300 miles above our heads. James Webb, we are not going to do that. James Webb is going to go much farther away, 1 million miles away from our planet. And we have never sent any astronaut that far. So if something goes wrong, we cannot go fix it. So we thought, okay, well, can we invent something so that James Webb can fix itself should something go wrong? So each of these mirrors can actually change position, they can actually move, they can change their shape even. So if something goes wrong, again, they can all move with respect to each other, okay, rotate, change the shape, and eventually the image will be just beautiful, wonderful. So no need to send any astronaut up there. It can do it by itself. And then before, this is an infrared telescope. Infrared is filled with heat. We are also releasing heat, right? If you touch your hand, you feel you are warm right now. That's infrared radiation that we are emitting right now from our body. Because James Webb is going to look, it's going to work in the infrared, we need the mirror to be much colder than the objects that we are looking at. And the temperature is something like 40 Kelvin, like minus 380 degrees Fahrenheit. Really, really cold. If James Webb does not achieve such cold temperatures, it will never be able to look at those galaxies that we are trying to see. So everything up here is going to be cooled down to 40 Kelvin. Also, we want to optimize the amount of light that we can collect. So the reason why the mirror looks yellow is because we laid a very, very thin layer of gold over each mirror. So that's really gold that we're sending up to space, laid on a structure of beryllium. There's a lot of stories behind this. Beryllium is a very stiff but also very lightweight material. And because we are going to cool everything down to such cold temperatures, it allows the mirror to retain its shape. When we warm things up, things change shape, right? When we cool things down, the same thing, they change shape. So we don't want that to happen here. So we picked beryllium to be able to just stay the way it is and allow us to launch this without too many problems. A fun fact, so if James Webb were on the surface of the Earth, it will be able to detect the light or the heat emanated by a candle that would be on the other side of the moon. Imagine how powerful it's going to be. Tiny candle on the far side of the moon. James Webb from here would say, hey, there's a candle right there. I see something. So that's how sensitive it's going to be. And it's going to see 1,000 times better than our own eye. So really, really powerful. So that's the eye of the telescope. But then I said behind, we can find the brain, right? Like our body, we have the eye and then the brain that processes all that information. So that's the brain of James Webb. It's really like 4 main instruments in their final configuration here. And the light will travel, will bounce back and forth in all these instruments here. And it will diffract, like I showed before. We'll get all this nice spectra, and we'll look at all the chemical composition of these galaxies. And these instruments also will provide a lot of, all the images and pictures that we're all looking forward to. They will look so much better than Hubble's. All right. This project's been going on for like over 20 years. It's been a headache for many of us engineers and scientists who have been working on this for such a long time. To develop such a telescope is really, really hard. There's a lot of new technology that had to be developed, invented from scratch, literally. And like I said, the mirrors, the instruments, something really, I think, good will be what we call the micro shutters. James Webb will be able to look at 100 objects at the same time. Hubble can look only at one object at a time. Actually, pretty much every telescope that we have right now can look at one object at a time. Like, we can do one observation at a time. With the micro shutters that are really tiny things like this that open and close like a shutter, James Webb will be able to look at up to 100 objects in the sky and allow 100 scientists at the same time to work with it. So not just one scientist at a time, but 100. So imagine the scientific productivity and efficiency that we will have with James Webb. The discoveries will come literally one after another. This thing's so tiny that it's like the size of a postage stamp, really tiny, like this. So from here we go to here to here. So these things are really, really small. And I mean, it took many years to develop technology like this. Not easy to open and close and then check, do they work really like we want? A lot of work has been going into this. And but finally, like I said, it's all done and built. Now so we talked about the mirror, the instruments, and now I want to talk about the sun shield. So James Webb is going to work at minus 388 degrees Fahrenheit, 40 Kelvin, really, really cold. In order to do that, the sun shield will have to protect James Webb from the radiation of the sun. The sun is a very hot star. The temperature on the other side is something around 180 degrees. It's still pretty hot. So we need something that will allow the temperature to go down from 185 all the way to minus 380. And we'll do it with a shield made of 5 layers. And here I colored all the layers with different colors, from red to blue to indicate that each layer will make the temperature go down little by little. So it's going to be done passively, just like a huge blanket, literally how we call it, thermal blanket, tiny, tiny blanket that will allow the temperature to decrease layer by layer. The size of the sun shield is like a tennis court, so 21 meters long. I think you probably get the idea of how big this thing is. And maybe you can start thinking or wondering about okay, how are we going to launch something like this? We'll get to it. Actually, that's a picture of the sun shield out in California. So that's where the telescope will be inserted, and that's like the blanket, and that's the size of a tennis court. Here I have some numbers. The thickness like 0.002 inches. Imagine how thin it is. And that thing has to, unfold in space and take the shape and remain like that for, years. All right, so our planet Earth, that's Hubble, 300 miles more or less above our heads. That's the moon, 384,000 kilometers. And then we have James Webb out here, 1 million miles away from our planet. That's basically 10 times the distance that separates us from the sun. So imagine how far we are sending James Webb. It's really far away. Like I said, we are not going to send any astronaut out there. But why do we want to send it that far? Why can we not keep it around the Earth like Hubble? Well, there are many reasons for it. So we are going to send in a very special point of the universe. That's very peculiar because in this particular point of the universe, anything that goes there will just follow the Earth in its motion around the sun. So James Webb, will just follow the Earth around the sun, okay, like this. Will always, basically point to our planet, and thanks to this, we can keep James Webb really far away from the sun. And actually, we don't like that because it's gonna heat the telescope. And that point here that we call Lagrangian point number 2 is also very good because it's a very clean orbit. So anything that ends up there basically cannot stay, will drift away in space. It's like being on the top of a mountain, on the very top of a mountain. If you have like a ball on the top of a mountain, you kick the ball is just gonna drop, go down the mountain, right, all the way down. There's no way you can, stop that from happening. So that's the same thing here. Anything that goes up there, okay, just a tiny, tiny perturbation will just make it go away. But, so you may wonder, well, then why do you want to put James Webb there? If, like you said, any minimal perturbation will send it away. No, that will not happen because we'll keep James Webb in an orbit, okay, around that point. But anything else, debris, meteorites, asteroids, space junk will just stay away from it. So it's, I think a smart choice to put something like this in the point of the universe. And then, like I said, it will allow us to communicate very easily with it without any interference. We have nothing apart from the moon in between. And then here, basically, I show that there are 4 other points like that, which we are not going to use, because here would be too close to the sun. Here it would be like having the sun in between, so we cannot talk to the telescope. And these 2 points here, L4 and L5, are actually the opposite. Those are like valleys. They accumulate, junk. So like, when the ball goes down in a valley, then it will stay there. And so here we really don't like to put much stuff in there, because then an asteroid can go there and hit our telescope or satellite and destroy it. So we are going to launch it from French Guiana, very close to the equator, with an Ariane 5 rocket. So that's one of the European contributions. And you can see here in this picture that James Webb is going to be folded. Yeah, we are going to fold it up in order to fit it in the rocket, right? So that's another challenge, and that's another reason why we had to make the mirror, made of smaller mirrors like that. So I said we're going to launch it, and eventually it's going to travel all the way out to its orbit. So this video here shows how everything will unfold and how it will reach orbit. Just a 1-minute video, and I will explain how it works. So after we launch it, the sun shield will be the first thing to deploy, because we are going to make sure that the mirrors will not warm up. We want to keep everything cold. Here you see how the sun shield is going to unfold. So layer by layer, it's going to open up like that. And that will start the whole cooling process. Down here we have a solar array that will provide power to the telescope, and an antenna that will allow us to communicate with the telescope. You can see here all the 5 layers opening up, and here we go. After we do that, the mirror will unfold and reach its final shape. So the secondary mirror, and then the wings, and here we are in its final shape. So it will take about 30 days to reach its orbit, and in those 30 days, James Webb will be busy doing all these maneuvers. So I think that video gave you an idea of how many things can go wrong. So just one little tiny thing that's gonna work the right way, and I don't know. We hope that will not be the case, but so this picture here shows actually how we assembled all the mirrors one by one. You can see some people here working on it. Really hard job here. That was in Washington, Maryland, where I work. So the test was there up to last year. Early, I think it was April 2017. So the mirrors were built one by one, and eventually assemble like this. And here you can see they are basically removing all the, the covers to get the telescope to have the final shape. The following video will show, actually will provide like a summary of like the whole story. It's a 4-minute video with music and audio, and I really hope you enjoy it. It really speaks to like how much work really has gone into this, and all that me and all of my colleagues had to do to do this. And by the way, I mean, I joined the project only like 4 years ago. There are people who have been working on this for over 20 years and have seen everything really from from scratch, all the way to what it looks like now. All right, so.
The efforts of thousands of people across the United States, Canada, and Europe for almost 2 decades achieved this milestone. The optical and science segment of the largest space telescope ever constructed stands complete in one of the largest clean rooms in the world, ready to endure its toughest yet battery of testing. Getting to this point wasn't easy. Never mind the logistic and construction challenges this international endeavor presents. Before astrophysicists' dreams of building Webb could be realized, 10 technologies that did not exist needed to be created and perfected. They were. To give you a sense of where we are in the mission, the Webb telescope consists of 3 main segments: the spacecraft bus, the sun shield, and the telescope, which includes Webb's instruments. This telescope segment of NASA's most ambitious space observatory stands complete and tall in the NASA Goddard Space Flight Center clean room. An international team of engineers built and tested this revolutionary telescope segment. Beyond spaceflight hardware, the Webb mission required building assembly structures, test facilities, transportation enclosures, engineering copies called pathfinders, and even a miniature test-bed telescope. Revolutionary, lightweight composite material capable of maintaining its shape to 1/10,000th of a human hair at temperatures near absolute zero forms Webb's backplane and science instrument support structures. Webb's mirror segments began as beryllium ore mined in Utah. They crisscrossed the United States to be formed. Lightweighted, polished, gold-coated, and finally, perfectly placed on the backplane structure with the help of a robotic arm. 4 state-of-the-art science instruments from NASA and its international partners, the European Space Agency and Canadian Space Agency, were installed and tested, each loaded with advanced components and detectors, and capable of operating at temperatures near absolute zero. Scientists will use these instruments to tease out answers to astronomical mysteries near the edge of the visible universe, in galaxies closer to home, around planets orbiting our star, and others like it nearby. The Webb telescope segment now stands complete. After launch phase environment testing at Goddard, this segment will endure more cryogenic testing at the NASA Johnson Space Center. Later, the telescope will travel to Northrop Grumman in Los Angeles to be mated to its sun shield and spacecraft bus. thus completing the observatory's assembly. The James Webb Space Telescope, our new eye on the universe.
So like you heard, a lot of testing clearly because we want to make sure everything just works before we launch it. So after all the integration of the mirror in Maryland, we took it down to Johnson in Houston, Texas, and we put it in there, in the chamber. The chamber that was used for the Apollo missions. And no, okay, I got a problem. Okay, no. The chamber was used for the Apollo mission here, and we put James Webb in there just a few months ago. And that chamber was used to simulate the space environment. So we cooled everything down to cryogenic temperatures. We pumped all the air out, so we made vacuum in it. And there it is, the real thing in the chamber. And the test was really successful. Everything worked just fine. So we have confidence that the mirrors are going to work properly. They're going to detect light, and the instruments are going to be able to use the light, analyze it. So it's a lot of challenges ahead of us. It came out of this chamber a few months ago, and it was shipped to Los Angeles and Northrop Grumman, where it is right now. It will be there for the next year and a half, two, before we ship it on a barge all the way down through the Panama Canal to French Guiana. So just like to say that we do a lot of testing, test everything, and build a lot of mathematical models that tell us, how everything works. Now that's really my job. I do the part on the right, the model. I do all the models, and then not all. I work with the models. I build them, I optimize them, and then I work with my colleagues that do the testing, make sure that my models and my colleagues' models are able to represent the telescope properly and are able to reproduce, its behavior the way it should. So, that's really how it is right now. You can see the telescope and the sun shield on the left. Actually, you can follow it live. We have a webcam, another no pun intended again, but it's really true. We have a webcam. You can follow it online, and you can see really what people are doing in real time. That's really cool. I'm actually done. The last few slides show how this technology development can have an impact on our daily lives. So, many people have asked me, okay, but we are building this just to learn about the first light. What happened like 14 billion years ago? Why? Sure, fair enough. So, okay, what we've done, for example, a lot of spin-offs. First, we're able to develop technology that we put on Hubble. So technology developed for Webb was used for its predecessor, Hubble, and made Hubble even better than it was. Hubble had like 5, I think, reparations in space. We went up there like 5 times to change its instruments and improve its capabilities. So we have a lot of technological spin-offs. All those detectors that we are going to, that we put on James Webb have become now the universal choice for astronomical observations, but also for Earth science and national security missions. A lot of commercial spin-offs. We have developed methods to test devices at cryogenic temperatures. And trying to, like I said, when we test things at these temperatures, one of the hardest things is to make sure that things don't move. So how can we remove the vibration effects from all this? So we created some way of doing it, so to test devices at very high speed. And as you can read my slide, we have created a lot of new technology and jobs in such fields as astronomy, aerospace, semiconductor, and even medical industry. And I'm going to actually close with this. A lot of medical applications that allow us to measure and diagnose ocular diseases and improve surgery, actually, eye surgery, or even to get detailed information about the shape of our eye in just seconds rather than hours. So patents keep being issued on this and other innovations driven by the GWST program. And I think many, many more to come. So that really takes me to the end of this talk, which I hope you enjoyed. Follow us live. And again, thank you very much to the Istituto Italiano di Cultura, Consolato Generale, for organizing this Italian Research Day all over the world, and to ISNA for its co-sponsorship. And I'll be glad to answer any questions you might have. Thank you.
First of all, thank you so much. It was an amazing presentation, absolutely stunning. I have two questions. First, you showed the graph, especially the Big Bang history, and there was a portion where you were saying about the very first expansion right before the Dark Ages, where you said that in a few seconds, in a fraction of a second, things traveled really far. So my first question is, did they actually beat the speed of light during that portion of travel? And then my second question is, do you think that telescope will be able to look into other life in the universe as well?
So regarding your first question, that's the inflation theory that was added to the initial Big Bang theory by Lemaitre. And it's something that I think we need to explain really what happened in a fraction of a second. It was confirmed by the cosmic microwave background. So maybe I can go back to the plot to show people what we are talking about. So the reason why we had that inflation, and then I will answer your question directly, is because, okay, so here, we couldn't explain otherwise why the universe looks so uniform here. So we sent a satellite in the 90s, Kobe, and then WMAP in 2003. They gave us a map of what we call the cosmic microwave background radiation in layman terms. Basically, these measurements told us that the temperature of the universe is something like 2.7 Kelvin all across the universe. So the universe has a very uniform temperature. Any point in the sky that we can look at, 2.7 Kelvin, 2.7 Kelvin. And suddenly we're like, well, how can that be if something like inflation didn't happen? So if things expanded very rapidly, very fast in that fraction of a second, okay, all the atoms and molecules were talking to each other, okay, still kind of remain close to one another in a way, during inflation, and so the information remained, uniform all across. So I think if we think of this phenomena in cosmological terms, I think things, could have traveled, faster than light. Here we need to distinguish between cosmological time and then the time, the way we measure it. So even if the universe is like 14 billion years old, the first galaxies, I think actually more than 14 billion light years away from us because of the expansion of the universe. So that adds, to the speed of light in a way. But I think inflation still remains a mystery in many ways. But it's a good explanation to this, the microwave background, this uniformity in the universe that we measure at that point. And a lot of people, some people won the Nobel Prize for this discovery. So, and then the second question is yes. So the fourth scientific priority of James Webb will be to look for life, the building blocks of life in the universe. So with James Webb, we'll be able to look at exoplanets, so planets that orbit other stars other than our sun. And you might have heard in the news with Kepler and TESS that we launched just a few days ago. Kepler will look at a lot of exoplanets. TESS will look at many more, and James Webb will be able to go even further than that to actually tell us the chemical composition of these planets, look at their atmospheres, and I think they will tell us a lot about what's out there, what's in those planets. Is there oxygen? Is there water? Is there carbon? Are the building blocks of life in those planets or not? So that question, that's still an open question. James Webb will definitely provide many answers to that. So we are looking forward to that as well. Sure.
Well, first of all, I too must thank you for the magnificent presentation, absolutely fascinating and formidable. And I also have two questions. The first one is, since what I heard of the last conclusions of astronomers and physicists is that the universe expands with accelerating speed and then contracts back and expands again, hence there was something before the Big Bang. What do you envision, or the contemporary physicists envision it as, what was there before the Big Bang? And the second question is about LISA, that it is tracking gravitational waves, and what do you envision them, and when do you envision them as being tracked, and how do you see them as looking and being captured by LISA?
Okay, so I didn't want to clarify that I'm not a cosmologist by background. I'm an engineer and I work a lot very closely with scientists and cosmologists. So clearly we know that we think that there is dark matter and dark energy in the universe, which is why we think that expansion of the universe is happening because of dark energy. The energy that we call dark because we don't know what it is, some energy that's somehow stronger than gravity, right? So the force of gravity pulls things toward a center, like we all are attached to the Earth because of the gravity that pulls us towards the center of our planet. So if there is gravity in the universe, there is, we have galaxies and stars, then why is the universe expanding instead of collapsing because of gravity? And so we said, well, there's some dark energy there that's stronger than gravity that's making the universe expanding. Now the question is, we don't know really. We haven't been able to quantify how much dark energy there is in the universe. And so is this expansion going to just, continue the way it has been doing so far, more and more, making the universe, expanding more and more, faster and faster, or rather there is some other mechanism, maybe due to dark matter, that will eventually kind of counteract the effects of dark energy and will make things slow down, and eventually, like you mentioned, make the universe collapse, and maybe another Big Bang will happen again, and then over and over. So these are actually the theories that I think we really do not have an answer for. And even if James Webb will not primarily look at dark energy and dark matter, but we have other missions coming up, like WFIRST, that will look at dark energy, dark matter, and will allow us to quantify these things a little bit better. And I think that's really what we need to know. You know, if you want to answer that question, is the universe continue to expand, or rather will stop eventually, will collapse again? If we don't know the answer to how much dark matter and dark energy there is in the universe, I think it's a little bit hard to answer that question. Now, I mean, so if there was there one Big Bang or more Big Bangs? What was there before? I don't really think we know the answer to it. Personally, I think I don't know. I mean, I get there and I kind of it amazes me. It really transcends my mind. It really amazes me. So if there was before, I don't know. That's what we have so far. We have a lot to learn. Even the Big Bang Theory still has issues that we haven't been able to fully resolve. Like that, it happens in the history of science all the time. That sometimes we think of something based on current knowledge, and we firmly believe that that's really the case. Then something pops up out of the blue. It's like, hey, and we are forced to revise our assumption, and then and that happened with the Hubble constant. The Hubble constant was not the value that we know right now. It was some other number, okay? And something had to come up to tell us, hey, try to look better. And that's how we found out about dark matter. So, and maybe something else will come up that will, allow us to tweak that number again. And like I said, we are open to discoveries, and there's still a lot to learn. The question was about gravitational waves. So LISA, it's a working project. So LISA will measure gravitational waves in space. So it will be a set of 3 little satellites put together in space and very far away from each other, and they will basically be able to detect these tiny variations in gravity in the space-time. The good news is that we have been able to detect some gravitational waves from the ground in the last 2 years, thanks to the LIGO and Virgo project, with a lot of Italian collaboration, by the way, into this project. So that was really an amazing discovery, the first detection of a gravitational wave. And then just a few months ago, last August, the gravitational wave coupled with a lot of what we call the electromagnetic counterparts. So it was not just like something that was moving our detectors. It was like a real gravitational wave associated with an event that was really happening in space. We detected X-rays, gamma rays, infrared radiation from this event. There was a huge press release, a lot of papers came out, right? So LISA will allow us to do this from space with greater accuracy. So without all the effects from the Earth and so forth. But we are a little bit far away from it. It's really hard to achieve that kind of level of accuracy in the measurements in space. And there were a few delays in the projects, and I think we are talking about the 2030s probably for LISA. So we have to wait like 10, 15 more years before we can see it up in space.
Would you expect gravitational waves from the Big Bang to look like, and when do you expect LISA to be able to measure?
I think, like I said, it's not my field of expertise. I think after we launch it, we'll have to wait for, I guess, for gravitational waves to kind of come by, pass by, and move. What they're gonna look like, I actually, like I said, I don't know. It's not my field, so some of my colleagues will be able to know. I mean, I know what they look like when they did the press release last year and 2 years ago. It looks all flat, and then you see bump, and then it goes down again. So that's clear what we were able to detect. I think they probably will look something like that, I guess. But to look at those gravitational waves in the very beginning, I mean, I think some experts will need to work on that.
I actually have an engineering question for you. You talked about the solar shields, the 5.
Yeah.
What provisions exist for protection of other types of burst radiation particles or electromagnetic? How other ways do you shield the device?
Oh yeah. Okay, the sun shield will primarily be like a thermal, will provide thermal protection to the telescope, and also protection from the orbital debris, meteorites, within certain limits. Then we have basically the instruments in the back, so all the electronics that's shielded also by other materials. It's not a thermal blanket anymore. Oh, the mirror just so it's a structure of so the back plane is a composite material, and then we have beryllium and gold, and we have thermal blankets around the edges of the back plane, but I think that's what we have. I mean, I think the sun shield will provide thermal protection from orbital debris, and then all the electronics will be like we call it like it's like space hardened, space hardened electronics. So I think that will that will be more than enough. I forgot to mention that will be the lifetime will be 5 years. Like got fuel for 5 more, so hopefully it could last as long as 10 years. Obviously the electron will degrade year by year. We know that the performance will degrade, but I think it will definitely be able to accomplish all the scientific goals that and meet all the scientific requirements without any problems. And I think the orbit's really clean. We know there's always stuff orbiting around, but that's all we can do by now. Yeah.
Thank you. Can you say who's paying for this whole development? Is it mainly the United States?
So maybe I'll show the picture. So all right. So here we have basically the sun shield, the mirror, and 2 of the instruments are United States. Then we have 1 European instrument, 1 Canadian instrument, and then the other European contribution is the rocket. Oh yeah. Yeah, so it's a long story, but long story short, the cap right now is $8.8 billion. That was the cap the Congress put on the project back in 2010 when we replanned the project. I think we're still under the cap right now. And so that should be the total cost of the mission. It's something around $8 billion only to build the whole telescope, and the other $800 million will be for operations in the launch and everything. So the cost covers everything all the way from birth to death. So that's sure.
Other questions? Well, I joined the other people in the public to thank you and to thank you for this really amazing, fascinating presentation.
Well, thank you all.